Hi, good afternoon, everyone. So this week we will talk about geometry. Recall that this is our second week on geometry, so hope that we can remember what we discussed last time. Geometry is something really important and actually really fun. A lot of students feel that geometry is challenging and get frustrated. I want to say it again, it's only because geometry has never been taught in the good way or even in the correct way in this country due to some math education reform since many years ago. That's very unfortunate, but trust me, if you truly understand what geometry is really about, and if you really work on proof-based problem, you will love geometry. Right now, geometry is kind of just a mix between true geometry and algebra, especially for math competitions. That's very unfortunate, but it is what it is. We'll see how we should work on those Mathcounts problem. It's not a surprise that every time you have a reasonably difficult geometry problem in either Mathcounts or AMC, even AIME, you get a lot of just calculations. Essentially, every time you have some algebra in it. So that's because you don't have a proof-based problem. You only have computing. Computing is fine. So let's work on the first problem. Find the formula for the area of an equilateral triangle with side length x. This is a very basic problem, okay? Everybody should actually memorize this formula if you do want to participate in any type of math competition. Okay, what is it about? So we have an equilateral triangle. We say the side length is x. So now we want to know the area. How do we do it? Well, remember last time we talked about all the just common triangles that are kind of special, right? We have 30, 60, 90 triangle in which we know some special property. This is 60 degrees, this is 30 degrees, and this is a right triangle 90 degrees. And why this triangle is special? Because we know the three sides in one square root of 3 and the 2 proportions relationship, because here the hypotenuse is twice of the shorter side, which faces the 30-degree angle. So if you actually connect the vertex at the right triangle with the midpoint of the hypotenuse, you will get an equilateral triangle here. Okay, this is a very important theorem, which is that if you, for any right triangle, if you connect the midpoint of the hypotenuse with the vertex of the right angle, 1/2 of the hypotenuse equals to this. This is actually a midline of the right triangle. So then you can see that this is an equilateral triangle. And because the hypotenuse is 2, this is 1, the longer side is, by the Pythagoras theorem, it's 2 square minus 1 square. Then take the square root, and this equals to square root of 3. So this is the 30, 60, 90 right triangle. And we also have the, let me switch the green pen. We also have the 45, 45, 90 special triangle, which is even simpler. In this case, the 3 sides are in 1, 1, and the square root of 2. This is obvious because this is equilateral triangle. So the 2 legs, if they are both 1, then the hypotenuse by the Pythagoras theorem must be square root of 2. So those are important. And finally, we have the equilateral triangle. And the equilateral triangle is just like this, what we have here. So today we're going to just derive a very important formula. That is that if you know the side length, what is the area? So all rows are 60, 60, 60s. Essentially, because it's an equilateral triangle, you only need to know one perimeter so that the whole triangle will be determined. That is side length. Once you know the side length, essentially the triangle is completely determined. So you should be able to compute everything, anything and everything related to this triangle. Okay, so how do we do it? Well, you really want to take advantage of what you have, right? You have a 60, 60, 60 triangle, so therefore you should be able to take advantage, say, what you already have. And it's very natural to look at this triangle because 30, 60, 90 triangle is kind of related to this, right? You already have a 60 degree there. So it doesn't take too long to realize that if you take this very important axis, this is essentially, it's anything you name it. This is the midline, this is the angle bisector, or this is the perpendicular, this is the height of the equilateral triangle. They are all the same thing. Essentially, if you take this perpendicular, this will be the symmetrical axis of this equilateral triangle. Essentially, you divide the equilateral triangle equally into two halves. Alternatively, you can do something like this, but that will be essentially a proportional thing, so we won't take that property. But you should know this is actually the same thing. In this way, you effectively just double the height, but that will involve some similarity, which is a little bit just kind of assume additional knowledge we have not talked about. So we just do a simpler thing. So in this is, we got a height. We already know the base. So all we need to figure out is what is the height. And what is the height? Well, because now we know the other side is also x. So by the Pythagorean theorem, we only need to know either this portion, what it is, then get the other leg by the Pythagorean theorem, or the other thing, but the other portion. But they are both the same. Both are 1/2 of x, right? So easily the height by the Pythagorean theorem, because this is a right, this is perpendicular, so this is a right angle. So by the Pythagorean theorem, the height h is x squared minus 1/2 of x squared. And without too much algebra, you can easily see, because you don't even need to do this, right? Because you already know this is a 30 degree, this is 60 degree. So you know the proportional relationship is right here, because this triangle gives you 1 to the square root of 3 to the 2. So the height and the hypotenuse here already in a 2 square root of 3 to root to 2 relationship. So h must be actually equals to 2 times square root of 3. Essentially, the denominator is 2, the numerator is square root of 3. This is the ratio. You need to be very good at ratios and proportions. So this is the 1 times x. Okay, if you do not see it, you just compute this. This is just exactly. You can factor out 2 x over 2 and easily see what this inside is. 4 minus 1, right? You just factor out 1/2 of x, because this is square, so you get a 4. And this one is just 1. So therefore, this is square root of 3. That's how we did this in the first place. It's exactly the same thing. So the height of this equilateral triangle is just this. Consequently, the area S is 1/2 times the base, x times the height, square root of 3 over 2x. Therefore, the formula is square root of 3 over 4x squared. That's the area formula for equilateral triangle. And everybody should memorize this, the coefficient. Of course, you always get the x squared term because that's how you already get the side length. So that's the x squared term. It's just by proportion. Every triangle, equilateral triangle should have this. So this is the formula. You just need to memorize, excuse me, square root of 3 over 4. And this is how we prove it is. It's very important to memorize this. Okay, very simple stuff, but you need to know how to do such fundamental computation. So let's look at the second problem. So we have a triangle. We have two angles. One is 45 degrees, one is 160 degrees. All right. If the side of the triangle opposite to 45 degrees, we know that side. Then what is that of the other, or the side facing the other angle, 120 degrees? So what we have here is 45, and we have a really big triangle. This is about angle. Sorry. This is about, oops. Okay, this is 45. And this is 120. You will be able to see what is this. This, of course, will be 15 degrees. Okay. So the problem is that you know the side of the triangle opposite to 45, which is this one. Let's call that ABC. So we know AC equals to 6 square root of 3. Then we want to know what BC is. Does this problem ring a bell to something that we actually discussed last 4 weeks ago in the last geometry lecture? Yeah, it seems that we have quite a few problems like this. We know two angles of a triangle, and those angles are kind of special. What angles are special? Anything related to 30 degrees, 60 degrees, 45 degrees, and so on, because they can give us special triangles. So in math, it's very important when you have a new problem, you don't immediately see the solution. Then think about another problem kind of similar to this, and you were able to solve, and how you solve it. Essentially, you just try to maybe adapt to your older solution to the new problem so that you can figure out the new solution. It just kind of gives you a hint there. Also, sometimes the problem can be actually very close, or sometimes you need to take one extra step, but it's still better than you start from scratch. This is a very important principle. That's why you do a lot of problems, right? You build some prior experience. You never start from a clean slate. If you don't do any problem practice at all, every time you face an even moderately difficult problem to you, it's a difficult, just a mountain to climb because you never did any exercises. Everything for you is new. That will be really tremendously challenging. But for your older prior problem, you do not memorize those solutions. You learn from those problems what is the ideas, what is the logic, what is the reasoning, and what is the fundamental kind of high-level philosophy or idea about that problem, not the specific mechanism or details of that problem. Also, those things are also important. So let's think about what we did last time. We have a few problems, remember, something like this. Well, remember problem 3 and problem 5 from last time are both something like this. Okay, we have to triangles, we know some angles about them, and those angles are special, like here, 30 degrees, 45 degrees, right? So each time we were able to draw a perpendicular from the vertex of the biggest angle. That way we immediately create two special triangles. One is 45, 45, 90 degree, and the other is 30, 60, 90 degree. And because those triangles are special, we only need to know one side, we can determine all the other side. That's exactly what we knew. We know one side of the original triangle, which happens to be a side of one of the two special triangles. Therefore, we were able to compute everything. Now, can we do the same? Well, let's see. If we draw a perpendicular, just like in those examples, we certainly get a 45, 45, 90 degree special triangle on the left-hand side, because that's what it is. We already had a 45 degree angle, but on the right-hand side, what do we get? We get a 15, 75, 90 degree triangle. Oh no, because 120 minus 45, that's 75. So this angle is 75. Also, this is not a random triangle, but this is not one of the triangles that we know there are some clear paths or shortcut to calculate all the related sides. This is not something we are looking for. So apparently, if you just blindly try to copy or mimic what you did with those two existing problems, it won't work. But still, the idea is very just helpful, very kind of enlightening. That is that you should be able to draw some auxiliary line to generate some special triangles. That's the high-level idea in those two problems, not just the specific method. If you just try to be a robot, copy a method that you knew it worked, but this problem is different. So it will fail you if you just being a robot. So you have to be creative and truly understood what happened last time. What happened last time was not really just about drawing the perpendicular. It was about, at a higher level, it was about drawing an auxiliary line to generate some special triangles. That's the high level idea. So can we do something the same? Well, we know 120 is special, right? Why 120 is also special? Because the supplement of 120 is 60. And 45, of course, is special. But how can we can use the fact that this is 45, that's what we just tried. We drew a perpendicular, get a 45, 45, 90 triangle. But in that, we have not actually used the fact that 120 is also a special angle. Remember why last time it worked? It's because when we drew the perpendicular, we simultaneously take advantage of the other angle. In this case, the two smaller angles are 30 and 45 in both cases. That's why you drew one perpendicular, it took advantage of both facts. But in this case, the other smaller angle is just 15 degrees. That's why it failed. When we drew the perpendicular, we merely took advantage of the other smaller angle, which is 45. But it didn't help that we have 15 at the other side. In other words, how can we do something that also takes advantage of the fact that 120 is also a kind of special angle? That naturally forces you to think about how do we take advantage of that. 120 itself is not special. What is special? It's its complement, right? 120 is a supplement. I'm sorry, it's supplement. The supplement is 60. Therefore, we may think about if we extend this, we will get a 60-degree angle. Now what? That's why geometry is interesting. You should always be very observant and kind of innovative. If this is 60, but this is 45, what we can do is extend this line and draw perpendicular from here. Why this will help us? Because now we create two special triangles, don't you see? If this is perpendicular from C, we call this D. Triangle BDC is a big 45-45 special triangle. Now, because this has to be 45, because this is 90, and therefore this has to be 30. So this is a 45-45-90 triangle. Because angle ACB is 15 degree, therefore angle ACD, not ACB, yeah, ACB, ACD equals to 30 degree, right? And this triangle ADC is a 30, 60, 90 degree. So at the very beginning, it seems that we got stuck. That's only because we try to blindly copy a known solution. Sometimes it works, sometimes it will fail you. In that case, you just need to adapt, okay, to the problem that you have. So now clearly we will be able to calculate everything, right? Because if you focus on this 30, 60, 90 triangle, what do you have? We have the hypotenuse. Then we can calculate everything. You know how to do it. We will be able to do, if this is the 6 square root of 3 AC, because AC equals to 6 square root of 3, therefore DC will be, which is the long side of the 30, 60, 90 triangle. We know the proportion between hypotenuse to this one is 2 to the square root of 3. So this is 6 square root of 3 times, you have to be very good at the proportion again and ratio. Know which one is which. Because this essentially is the square root of 3 side, and the hypotenuse 2 side, the ratio is square root of 3 over 2. So it times the hypotenuse with this one, okay? Not the other way around. Make sure that you know when you do the proportion which one is which. Don't get flipping. Don't get just reverse the numerator and denominator, okay? So this would be 3 times 3 equals to 9. And therefore, BD is also 9. But at the same time, you can get AD. Clearly, AD is just 1/2 of AC. That's just 3 times square root of 3, just 1/2. This is the shorter side of the 30, 60, 90 angle. Therefore, AB equals to BD equals to 9 minus AD, minus 3 square root of 3. And that's what AB is. But we are not required to do that, did we? So we were required to do BC, but BC is simply a square root of 2 times BD. So it doesn't really matter. So BD actually is, what is DC? Well, DC is right here, so it's 9 square root of 2. Okay, that is actually the solution. We were supposed to get BC, not BD. Oh, I'm sorry. So it's BC. BC is what we need to get, right? The end, the side, and make sure it faces. Yeah. The side facing the 120 degree. That is this one. Okay. So the takeaway is that when you do any math problem, you need to kind of follow certain well-studied principles. Here, we try to learn from what we did before, but not just blindly copy it. We try to make a connection, and based on that, we figure out a closely related but a kind of new way of solving the problem. Here, instead of blindly drawing a perpendicular, we extend BA. Then draw a perpendicular from C to this extension, get an intersection point at D. That way, we both create a 45, 45, 90 triangle, which is a BDC here, and a 30, 60, 90 degree triangle. This type of kind of reasoning and logical thinking is very important in any mathematical problem, but particular geometry gives you a very fertile field for you to kind of develop and nurture this type of skills. Okay? Very important. Okay, let's talk about next problem. Oh, how to do the Heron formula. Okay. This is the Heron formula. What is Heron formula? If you know a triangle generally with three sides ABC, oops. So ABC. It's important to understand that once you know the three sides lengths, that's A and B and C, the whole triangle is uniquely determined. Why? Because by the side congruence, all such triangles are the same. You have all the three sides being equal to the other three sides of another triangle. The two triangles must be congruent. Therefore, the triangle is actually fixed. You cannot change it in any way. There's no freedom for modification. So, we should be able to know or compute everything, anything related. For example, what is a midline? Well, that's advanced geometry. So you need a formula to get that, but that's not for Mathcounts. Essentially, once a triangle, you know all the information about triangle, then anything related to that triangle must be also determined. Not just from a kind of just a philosophic perspective, right? You know anything can be calculated. In this case, what is the area? Well, that's why you have a Heron's formula. Heron's formula says that the area is S times S minus A, S minus B, S minus C. And what is S? S is just 1/2 of A plus B plus C. Okay, that is the famous Heron formula. And, oops, I guess, yeah. So, this is Heron's formula. Okay. So, use Heron's formula to find the area of an equilateral triangle with side length of 4. And do this with problem 4. That is, okay, use this formula, right? Well, we just try to do some quick exercise. If an equilateral triangle side length is 6, use Heron's formula. What is the area? We know S is the three sides. They're all the same. Add up to 18 divided by 2. S equal to 9. Right? Okay, what is the area? Just plug in the Heron's formula. That's 9 times 9 minus 6 they are all the same. So 3, 3, 3. Oops, too many 3's. What is that? This is 3 to the 5th power take square root. So it's really, you can factor the 9. That's 3 to the 2 twice second power, which is 3 squared, right? You get this guy out. So what is remaining inside the radical is just 3. So the area is 9 square root of 3. What is the formula we developed earlier? That is square root of 3 over 4 times 6 squared, right? That's the side length. And what is it? 60 squared is 36. 36 over 4, that's exactly 9. So this is again 9 square root of 3. So the two are apparently equal. Not surprising. That's what it should be. So that's how Heron's formula can tell you. All right? They are the same. By the way, everybody should be able to independently derive the Heron's formula. Okay? This is a very important formula, especially in middle school math competition. From time to time, you will use it. Also, I'm not sure they're expecting you to know it, but it's really important to remember Heron's formula. And it's not that difficult. There are many more interesting problems related to triangle that will ask you to compute anything that involves the law of cosine, but effectively how to derive Heron's formula, you follow the basic principle when you deal with law of cosine, which I'm sure we don't need to discuss, but essentially you draw a perpendicular, do some algebra. Because you know A, you know B, you know C, let's assume this is a acute triangle. If you have a obtuse triangle, it's similar, but we can always choose, we draw perpendicular from the largest angle so that the height, the altitude will always lie inside the triangle, instead of outside the triangle. That's a kind of special trick. We can always assume we are drawing the perpendicular from the largest angle's vertex, so that the other two are smaller acute triangles. When you do this, what do you have? You create a new variable h, right? That's the altitude. We don't know what it is. We know it's the altitude. At the same time, you divide the other side, c, into two portions. Did we create two variables? No, we just created one because we know their sum is c. The two are not independent. So if we know y is x, the other must be c minus x. The same thing if you know the other is x, so you get the other side is c minus x. So we truly created two variables. One is a portion of the base, one is the height. How many equations can we write? We certainly know how to write the two equations, because with this altitude we get two, not just one, two right triangles, right? So this is right angle, this is right angle. Therefore, we are able to write two independent. It's very important to recognize that two are actually independent. Two independent equations. So a squared is one hypotenuse equals to h squared plus x squared, and b squared, the other right triangle, h squared plus c minus x squared. So therefore, in theory, all we need is just do some mathy algebra. We have two equations, we have two variables, we are able to solve them. So all you need is just solve h. Then the formula for the area would be 1 over 2 times c times h. Whatever h you get from this not so easy system equations, you will be able to plug it in. Okay, that's the general approach. So we are not going to do that, but everybody should know all the detailed steps doing this. Okay, this is a very simple problem. Why? All you need is to keenly understand what we are doing and have some good mathematical sense. So the areas of three faces of rectangle box. Okay, so it's a 3D scene. Those three numbers: 18, 75, 24. What is the volume? It's super easy. So if we have rectangle box, something like that, we know the three of dimensions. Let's call them A, B, C, essentially. The three faces, different faces, what are the areas? It's AB, AC, and BC, right? It's not that difficult to see. Let's just call this is A, this height is B, this length is C. So we know those three. Let's use a color. So clearly we have we have 6 faces in total. And there are 3 pairs because any 2 faces directly opposite, parallel and opposite to each other, they are the same, of the same dimensions. For example, this guy is the same in terms of shape. 2 congruent, they are opposite, parallel to each other. So we only have 3 different pairs, and the areas are A, B, BC, and AC. We know those are 3 numbers. They are 18, 75, and what? And 24. We don't have to, we can randomly just say this is this, because we don't care about which one is which one. They are just symbols, right? A, B, C. Doesn't matter which one is which. But now what is the question? Question is that what is the volume of this box? Well, we know the volume formula is just A times B times C. But by now, we are 7 weeks into this training. You should know this can be written in terms of those 3 quantities. And it doesn't take too long to see. It's just square root of multiplying those 3 together, right? AB times AC times BC, because each variable appears exactly twice, because those 3 products are cyclically symmetrical. So when you multiply all of them together, because of this cyclic symmetry, every variable will appear exactly twice. So this is really ABC squared, and that's why this is it. So the volume is very easily, it's 18 times 75 times 24, and you do the rest. That's very easy to do. Just be careful you do a good job. For example, a quick way to do this is 18, we know that's 9. 9 is a 3 squared, so we can quickly factor that out. 75 gives us 25. 25 is 5 squared, so we quickly get the square root of that out. So inside the radical, 18, you get out the 9 factor, there's 2 remaining. 75, you get out 25 factor, you have a 3 remaining, times 24. And you should be able to notice that this is also very easy. 2 times 3, that's 6. 6 times 24, that's 144. 144 is 12 squared, therefore this is 3 times 5 times 12. Easily, 3 times 5, you can times 5 with 12 first, that's 60. 60 times 3, that's 180. So what I'm saying here is that if you want to do math competition, one of the basic skills you can easily develop, well, not easily, but it takes effort, but it's not that difficult, let's just say it that way, is to develop your number sense. How to compute with basic multiplication, division, square root, all that. You need to memorize subject to a certain number. That's typically say 25, all the perfect squares. What is 13 squared? That's 169. What is 17 squared? That's 289. And so on. What is 23 squared? That's 529. All those things you should be very familiar with. Why? Because when you do math competition, all those little things will help you. Can help you here save 10 seconds, there save 5 seconds. But so many problems, everywhere you save a few seconds, collectively, you'll become a much better, much quicker, much more accurate mathlete. Alright? If you never do any practice like this, each problem can take you a lot of time. Even you can do all those problems, you are only able to finish, say, 20 out of 30. Well, the other guy can do, say, 26. Maybe the last 4 problems are too challenging. But that's a huge gap there, only because you are slower. Okay? So training is very important. Develop some fundamental basic skills, also very important. Not just because they will make you a quicker, more accurate student. It can also stimulate your mathematical thinking, just kind of reasoning capabilities as well. Once you develop very good number sense, okay? All right. So let's look at the next problem. Okay. The sum of the lengths of the 12 edges of a rectangular box. Whoa! Didn't we just have that? A rectangular box. So maybe we should redraw that box. So we have rectangle. We have 12 edges. We know we only have 3 different sets, right? Because that's ABC. We have 4 A's, 4 B's, 4 C's. For example, if this is A, then we know this is A. This is also A, and this is A. Similarly, this is a B, this is a B, this is a B, and this is a B. And this is a C, this is C, this is a C, and this is C. So we know those 12. The sum of the lengths of it is 92. Okay, so we know 4 times A plus B plus C equals to 92. That's the first formula we can quickly write down. The surface area. Okay, what is surface area? Surface area, as we just saw from the last problem, we have 6 surfaces and there are 3 pairs. Each pair has 2 identical ones. So 2 times AB plus AC plus BC equals to what? 240. And what is the question? The question is, what is the length of what? Interior diagonal of the box. Okay, we need to draw a diagonal box from this vertex to this vertex. Does anybody know what is this? Well, this is a standard trick, right? You have to know what is the diagonal of a rectangular box. Okay? For that, you should know something really fundamental. It's the square. Oops. It's a square root of a squared plus b squared plus c squared. This is nothing but using the Pythagorean theorem twice, because all you need to know is just to first you get a kind of a diagonal plane. To think about it, you cut from this plane. So it's like this. You make a perpendicular cut. Cross this section, this will be rectangle, right? The rectangle here is nothing but just like you have a cake, square, rectangular shaped cake. That's weird, but it is what it is. You make a perpendicular cut where you can easily see that you get a kind of diagonal plane, which itself, that intersection is a rectangle. The height remains a, but a new side, which is the diagonal of the top surface, just top surface square, that will be square a square plus c square, right? So this one is square root of a square plus c square. And now you do the final diagonal of the new intersection rectangle, that is the square of this guy plus b, so b squared, then take a square root of the new one. So essentially, you recursively use the Pythagoras theorem twice. So first time, get an intersection of the perpendicular intersection surface plane for the rectangular box, then that itself is a rectangle. Then use the Pythagorean theorem again to get the diagonal of this intersection rectangle to get the really rectangle, the diagonal you were asked to do. So easily this is a squared plus b squared plus c squared. So now you can see that this is what? This is actually algebra problem. We talk about this in one of our algebra week. Essentially, you have two formulas or two equations. A plus b plus c equals 23. That's from this one. And you have ab plus ac plus bc equals to 120. Those two equations are not going to be sufficient for you to solve a and b and c individually, because you have two equations, but you have three variables. But that's not what we need either. We don't need to know A or B or C. We need to know what this animal is, right? And we know, essentially, we were asked to manipulate algebra somehow to derive this quantity from the two known numbers. And of course, easily, you see that we are truly being asked to calculate what is a squared plus b squared plus c squared, because after that, we just take a square root. How to get it? Well, apparently, you should think about taking square of this, because that's the only way to get those square terms, right? And you should memorize what is the formula for this one. A plus b plus c squared. What is this? This is trinomial square. We know binomial square, but if you will perform math competition, you need to know a little bit more, right? It's not too much a requirement for everyone to memorize what this should be. You can derive it on the spot, but if you do that, you are wasting a lot of time. Everybody should memorize what is a trinomial square. So this is because this is the squaring of a trinomial. 3 times 3 equals to 9. So before you combine similar terms, this squaring should give you 9 terms. But we have some combination to have. So this is actually a squared plus b squared plus c squared plus 2ab, 2bc, 2ac, and 2bc. This is the trinomial squaring formula. And it's very easy to derive this. Okay, not that difficult. You just expand it. You just put this into a matrix like this. So this is 3 by 3. So, right? This is A, B, C, A, B, C. What do you have? But the distributing property give you get a squared here, you get AB, you get AC, AB, B squared, BC. this is just a kind of help you to understand this very quickly, but you can do the actual algebra. So you can see that when you add rows 2, you will group rows 2 together, group rows 2 together, and finally group rows 2 together. That's why you get this formula. Isn't this already what we wanted? Once you know the square, this term is exactly twice of this term. So you immediately get this by subtracting this from the square root of 23. So a squared plus b squared plus c squared really is take square of 23, that's 23 squared, minus 2 copies of 120. Okay, so that's how easy this is, because Mathcounts really don't test you. They will not give you a problem that will require you to think, say, half an hour. Usually just a couple of minutes. So it's 1 or 2. Rarely you need to do 3 tricks together. But even if you need to, those tricks are usually very well connected. It doesn't take that long. So once you recognize this, everything should be. What is 23 squared? Everybody should immediately tell it's 529. Once again, you need to be very good at those fundamentals. 23 squared is 529. So you are subtracting 240, I'm sorry. So what is this? This is 289. Okay, what is 289? It's 17 squared. Therefore, what we know is that if we take square root of this, will give us 17. And that is the diagonal you're looking for. Okay? So, if you truly know all those small tricks, you can do this problem very fast. But even if you know how to do this problem, every step of the way, you need to spend a lot of time. For example, what is 26 squared? I have to do it by hand. That's 69, that's 46. Even if you do this very fast, you waste a lot of time. What is a plus b plus c squared? That takes me 2 minutes to figure out. You are doomed. You cannot do well. Even you are so smart, you solve this problem in 15 minutes. It shows one thing. You are still mathematically strong. You know you can eventually figure out all of this by yourself. That's remarkable, no doubt about it. But Mathcounts, unfortunately, is a math competition, or just AMC, the same thing, require you to be very fast. So all those things should be part of your arsenal. It's in your toolbox. Whenever you need it, you can grab it, immediately get a result. You don't have to redevelop those tools on the spot. Okay? This is really important. It's the same thing in any competition. Okay? Let's just say if you run a marathon. I never train for a marathon. Okay, here I'm the race. Everybody wait for me. Give me half a year. You wait for me half a year. Let me train. Then I will compete with you. No way. You have to start in that just kind of just within the maybe 8 hours window to complete this race. Nobody will wait for you for half a year to develop your muscles and endurance, then compete with you. So you have to develop all those tools, make them immediately available during the real math competition. That's why it's important to train for basic things, okay? Okay. Whew. This problem actually is fairly easy, all right? So in this figure, we know BC and AD are both perpendicular to AB. Everybody should immediately know, because they are both BCAD perpendicular to AB, they are parallel, right? So, and BC BC equal to AD. So this is really just part of okay. If you actually connect, this is CBA, this way. That's why it's written that way. ABCD. This is ABCD is actually a rectangle. Okay, so you already know AB is 12. This is 8. What is the problem? The problem: how many square centimeters are shaded? Come on, that's too easy, isn't it? Because when you do what is shaded, it's much quicker to do this triangle first and then subtracting it from the total area, which is a rectangle. You already know the width and the height, the base and the height. So this is 12 times 8 minus what? 1/2 of it. 1/2 of itself. So why? Because this is a triangle that has the same base, same height. It's just a triangle, so it's 1/2 of the rectangle. So shaded area is just 1/2 of the rectangle. So immediately, this problem, if you are really solid in basic geometry and all those things, you can solve this in 30 seconds. Agree? All we need to recognize is that this is a rectangle. Why? Because BC is perpendicular to AB, and AD is also perpendicular to AB. So you get 90 degree here, you get 90 degree here. Therefore, BC is parallel to AD, but BC also equals to AD. They're both equal to 8, isn't it? So that means that this is a parallelogram. But the parallelogram, you have an angle that is 90 degrees. So this is not just any parallelogram, it's a rectangle. All those things should happen in your mind under 15 seconds. That's what you need for math competition. Because those things are too, yes, to some student who doesn't like geometry, every step of the way is difficult. But for math students, everything should be so obvious. That's why you need to develop solid basic skills. It's just like, did you ever watch a video where Michael Jordan shoot a free throw with the eyes blinded? He covered his eyes, he shoot a free throw and he made it. I'm sure Steph Curry can do the same thing. But ask Shaq O'Neal to do that. Oh my goodness. So this is just really 1/2 of 12 times 8. All right? Apparently that's 48. So it's a very easy problem if you can know the basic things. On the other hand, if you want to just kind of say, I want to know what is, use the area formula, I need to compute this, then compute this. Actually, you can. The problem never gives you enough information to determine that, because you never know where this point. It could be here, it could be here, because it won't change the nature of the problem. The number so given, it's indeterminate as to where this point is located. Okay? If you want to blindly use the formula for the two right triangles, you'll never solve this problem. The only way to think of it is recognize that the total area of the shaded area is just subtracting this area. But it doesn't matter where this point is located. This green shaded triangle always have the same area. That's the gist of this problem. And it just really requires you to recognize the basic things. All right. The last problem. Well. You watched the video, right? Were you confused? How did Richard solve the problem? Well, you have a trapezoid. You know the top base and the bottom base. I believe is 20 and 30. So always remember, whenever you have something like this, you immediately get a pair of similar triangle, right? So because of trapezoid give you a pair of parallels, immediately you get those two triangles similar to each other, because this angle is congruent to this angle, and this angle is congruent to this angle. Of course, the vertical angles are always congruent, so therefore immediately have a pair of similar triangles. And this, of course, the problem asks you to calculate, if you know the total area, you need to calculate the area of this triangle. But that is not seen through two kind of just a proportional reasoning. Okay, so you calculate in the problem, you first calculate this triangle. By the way, proportional reasoning is very important because in Mathcounts AMC you are always to calculate something, not to prove something, but it's the same underlying mathematical theorem at work. Use proportions, first get this bigger triangle, and then because now once you know the bigger let's just call this ABCD. Okay, so once you know the area of BCD, you recognize that you get the blue part based on a fraction or proportion between those two sides, because they share the same altitude. It's just the base proportion. That will give you the area of the blue highlighted triangle. So you take proportions in two steps, get the blue highlighted triangle area. But what is the problem? That's what happened in the video when Richard taught this problem. Oops. This is actually a very smart way of thinking things. So in this figure, Richard essentially to just put a lot of identical or congruent trapezoid, combine them into such a mosaic. And with the proper coloring, because the four little triangles in the trapezoid are colored with four different colors, right? Red, blue, green, and yellow. And clearly, when you combine them in this way, expanded in a row, then stack multiple rows together, this is into this such a mosaic, you can see that we're required to get the blue triangle's area, right? If you look at a parallelogram, which is kind of, let's just say, having four yellows, little parallelogram, yellow parallelogram at the four corner, with the bigger red parallelogram in the center, and the four sides with two pairs, two rectangular, non-rectangular parallelogram in green and the two parallelogram in blue. Essentially, you look at the bigger one. So essentially, or you just look at four colors: red, green, yellow, and blue. What do you get? You get exactly twice of each triangle, right? You turn your head, say by 45, almost 45 degrees. Look at this like grid-shaped mosaic. It's just very the shape is very unique. You just take a look at, say, take a parallelogram which constitutes 4 parallelogram for different colors: blue, yellow, green, and red. Then you will see what the total area of this new parallelogram is exactly twice of the trapezoid, because you have 2 copies of each colored triangle. And how did you do? Say, I want to know the blue triangle's area. I just need to know what is the proportion between this blue parallelogram to the overall parallelogram, right? So if you think about it, if you look at this, what happened is something like this. Okay, I'm gonna color each one just exactly like what is in this figure. So blue, then we have yellow, red, and the green. Okay, so this would be yellow, and this would be green, and finally this would be red. So that's exactly how this will look like. You turn your head by about 45 degrees. Okay? Agree? And where's the trapezoid? The trapezoid was right here. Yeah, diagonal. The trapezoid was right here. Okay, that's what it is. It's a very clever way to have kind of no, just a proof without words type of thing. So now you figure out what is the blue's area. It's a fraction of this. You just calculate what is the fraction in terms of this one compared to this one, and at the same time, what is a fraction of this side to this side, right? Because this is all based on proportional reasoning. Because this parallelogram, let's just say this one, what is the area of this just parallelogram? It's a fraction of the overall parallelogram based on this proportion. Once you know that, you can similarly calculate the blue one out of this. But what are those proportions? That's exactly 2 over 5 and 3 over 5, because you can see that, let's just say focus on the first one. What is the proportion between this one and this one? That is really what is the proportion between this one and this diagonal, right? So because they're all parallel to each other, you can see that. So it's really what is the proportion of this side over this side. Once you know that, you do the other one similarly. What is this one over this one? So where do they come from? It all came from this similar pair of similar triangles. Because if we know, say, this one to this is 2 to 3, as we know it should be, this is 20 to 30, so this is 2 to 3. So if we want to know what is this proportion for this overall, it would be 2 over 2 plus 3, right? 2 over 2 plus 3. And what is this over this? This will be 3 over 2 plus 3. So quick and easy. So this is truly a proof without words. But it's a very clever way. Also, I would make a comment. This is very cute and smart, but generally this is not how you solve a geometry problem. Once you solve the problem through an orthodox way, you will think a solution like this, well, this is cute. But I'm not so sure everybody should, even during just a non-time constraint math competition, should think about problem like this. It just shows geometry can be really fun. Okay, that's it for this week. I hope that you have a great week. We will see you on Sunday again. All right, bye.